November 5, 1941. Bureau of Ships, Washington, D.C. A British delegation sits across from American naval engineers, describing an impossible problem. They need a ship that can cross the Atlantic Ocean in winter storms, then run itself onto a French beach and unload 40 Sherman tanks in under 2 hours. Not at a dock, not with cranes, directly onto sand while German artillery shells are landing around it. Every shipyard designer in America will look at those specifications and say the same thing. Physics doesn't work that way. You need deep draft for ocean stability. You need shallow draft for beaching. You cannot have both. It is a mathematical contradiction, like asking for a square circle, but sitting in that conference room is a 47-year-old engineer named John Niedermeyer, who spent his entire career in preliminary ship design at the Bureau. And within 3 days, he will sketch out a solution so radical, so fundamentally wrong by every conventional shipbuilding principle, that senior naval officers will initially refuse to test it. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. They will argue that intentionally driving a ship onto a beach at full speed violates 18th century naval regulations about running vessels aground. That sketch will become the landing ship tank, the LST. Over 1,000 of them will be built in 3 years. They will land more armored vehicles on hostile shores than every other method in human history combined. Without them, Dwight Eisenhower will later say, the invasion of Normandy would have been impossible. The entire Allied strategy would have collapsed. But in November 1941, none of that has happened yet. Right now, it is just one man with a pencil, staring at an impossible problem, about to break every rule in the book. Let us go back to understand exactly what problem he was solving and why every traditional solution had already failed. The British learned about amphibious assault the hard way. Gallipoli, 1915. They tried landing troops on Turkish beaches using rowboats and small steamers. Soldiers climbed over the sides into chest-deep water while carrying 60-pound packs. Turkish machine gunners simply waited. By the time men reached the beach, entire companies had been slaughtered in the surf. 25 years later, nothing had fundamentally changed. In 1940, at Dunkirk, the British evacuated over 300,000 troops from French beaches, using destroyers, fishing boats, private yachts, anything that floated. But they left behind all their heavy equipment, every tank, every artillery piece, every truck, because there was no way to drive vehicles off ships onto beaches. Standard cargo ships required docks with cranes to unload. Landing craft could carry troops but not tanks. The few specialized vessels that existed, British LSTs, landing craft tank, could carry several tanks across short distances, but were too small and unseaworthy for ocean crossings. They had to be transported to invasion sites on larger ships, then offloaded. The entire process was cumbersome, slow, and vulnerable to enemy interdiction. Winston Churchill understood the mathematics immediately. To invade continental Europe, the Allies would need to land armoured divisions directly onto defended beaches, not near ports. The Germans would fortify every port heavily. The invasion had to happen on open coastline, where defences were weaker. That meant ships capable of crossing oceans, approaching hostile shores, running themselves onto beaches, and disgorging tanks that could drive directly into combat. In August 1941, at the Atlantic Conference in Argentia, Newfoundland, President Roosevelt and Churchill met secretly to coordinate war strategy. Britain was fighting alone against Germany. America had not yet entered the war but was providing massive material support. One of Churchill's urgent requests, help us design ships that can land tanks on beaches. The survival of Britain and the hope of liberating Europe depended on solving this engineering problem. The problem seemed unsolvable. Every naval architect who examined the requirements hit the same wall. Ocean-going ships need deep keels for stability in rough water. A freighter draws 20 to 30 feet. Even a destroyer draws 15 feet. But beaches slope gradually. To get close enough to unload, a ship needs to draw less than 5 feet, ideally 3 feet or less. Standard naval architecture said you could not have both capabilities in one vessel. The British had tried HMS Boxer, HMS Bruiser, HMS Thruster, built in 1941, were their first attempts at ocean-going tank landing ships. They could carry 13 Churchill tanks and cross the Atlantic at 18 knots, fast and capable in deep water, but they drew too much water to beach properly. Each had a very long ramp, over 90 feet, that extended forward from bow doors, trying to bridge the gap between the ship and shallow water. The design was compromised, slow to build, expensive, and complex. The ships took until early 1943 to complete, partly because German air raids on Belfast disrupted construction at Harland and Wolff. The urgency was intensifying. The British also converted 3 Maracaibo-class lake tankers into tank landing ships as an interim measure. These Venezuelan oil tankers had been built with shallow draft to cross the restrictive bars of Lake Maracaibo. British engineers cut off their bows, installed bow ramps, and scooped out the interiors to carry vehicles. The conversions were ready by August and December 1941, but they were slow, limited in capacity, and clearly stopgap measures. Something better was needed, and fast. By November 1941, with America on the brink of war, the British Admiralty sent a delegation to Washington. They needed American shipyards to mass-produce invasion ships, but first they needed a design that actually worked. The specifications seemed impossible. The ship had to be large enough to carry at least 20 Sherman tanks, each weighing 33 tons. It had to have enough fuel capacity for transatlantic voyages, potentially 9,000 miles of range. It had to be seaworthy enough to survive winter storms in the North Atlantic, where 40-foot swells were common and November gales could tear poorly designed vessels apart. Then it had to be able to approach a beach, reduce its draft to less than 4 feet, run itself aground, open its bow, drop a ramp, and let tanks drive directly onto dry sand. And one more thing, it had to be cheap enough and simple enough to build by the hundreds, maybe thousands, in shipyards that had never built ocean-going vessels before. Every established shipyard on both coasts was already building destroyers, cruisers, aircraft carriers, submarines, cargo ships. There was no excess capacity. Somehow, the LST program would need to find construction facilities that did not currently exist. John Niedermayer was appointed Technical Director of Preliminary Ship Design specifically to tackle this problem. He had worked at the Bureau of Ships for years, designing everything from destroyers to cargo vessels. He understood hull dynamics, weight distribution, stability calculations, all the formal mathematics of naval architecture. Ships were his life's work. But he also understood something more fundamental. When you cannot satisfy contradictory requirements simultaneously, you satisfy them sequentially. You do not build a ship that has both deep draft and shallow draft. You build a ship that can change its draft. The solution was ballast. Submarines already used this principle. They flooded ballast tanks with seawater to submerge, then pumped them out with compressed air to surface, changing their buoyancy dramatically. What if you designed a surface ship with massive ballast tanks that could be filled for ocean travel, giving it a 14-foot draft for stability, then pumped dry for beaching operations, raising the hull until it drew less than 4 feet? The mathematics were brutal. To raise a ship that much, you would need ballast capacity equal to nearly half the ship's displacement. That meant enormous tanks taking up space that could otherwise carry cargo. It meant complex pumping systems capable of moving hundreds of tons of water in about 2 hours. It meant the ship would ride dangerously high in the water when ballasted out, making it top-heavy. Engineers would need to carefully calculate the center of gravity and ensure the vessel remained stable in both conditions. But it would work. In deep water, flood the tanks, the ship sits low, stable, able to cross oceans. Approaching a beach, pump out hundreds of tons of seawater. The ship rises like a surfacing submarine, its draft decreases, and it can run right up onto sand. Niedermayer sketched it out in 3 days. The drawing looked wrong to anyone trained in conventional naval architecture. The bow was blunt, almost flat, completely unlike the knife-edge prows of destroyers and cargo ships. Sharp bows cut through water efficiently at speed, minimizing drag. This bow would push water like a bulldozer, creating massive resistance. But this ship was not designed for speed. It was designed to be beached. A blunt bow would ride up onto obstacles rather than ploughing into them and sticking. The hull was flat-bottomed, another violation of standard practice. Normal ships have V-shaped or rounded hulls that slice through waves. Flat bottoms slam into waves, producing a miserable ride. Sailors would hate it, but a flat bottom distributes weight over a larger area when beached, preventing the ship from sinking into soft sand. And it allows the ship to sit upright when grounded, rather than listing to one side, making unloading far easier. The beam, the width, was enormous relative to length. Normal ships have a length-to-beam ratio of about 10:1. Like a destroyer, this design was 6:1, almost as wide as an apartment building is tall. That made the ship slow and produced terrible handling characteristics in rough seas. It would wallow like a barge, rolling sickeningly in storms, but it also spread weight over a huge footprint when beached and created immense internal volume for cargo. Most radical of all were the bow doors, two massive hinged steel doors at the bow that swung open outward, each 14 feet wide. Behind them, a ramp that dropped down onto the beach. Tanks and trucks could drive straight out the front of the ship. No cranes, no climbing over sides, just drive off and go directly into combat. Niedermayer sent the rough sketch to the British Admiralty on November 5, 1941. They approved it immediately. This was exactly what they needed, however ugly and ungainly it appeared. The Admiralty requested America build 200 of these ships under Lend-Lease for the Royal Navy. The Bureau of Ships began refining the design. The initial plan called for a ship 280 feet long. Engineers ran calculations and realized it was too small to carry sufficient ballast and cargo. By January 1942, they had stretched it to 290 feet, still not enough. By February, final specifications called for 328 feet long, 50 feet wide. This was no longer a boat. It was a floating warehouse with a ramp at one end. The internal layout was pure functionality. The tank deck, a vast open cargo hold, ran the entire length of the lower hull from stern to bow, 300 feet of uninterrupted space, no bulkheads interrupting it. Just one enormous cavern where up to 20 Sherman tanks could be parked and lashed down, or 40 smaller vehicles, or 2,000 tons of supplies. The tank deck's ceiling height was 11 feet, enough for any military vehicle in service. Above that, the main deck, where lighter vehicles and cargo could be stacked, trucks, jeeps, artillery pieces, supplies. Initially, an elevator lifted vehicles from the main deck down to the tank deck, but engineers quickly realized the elevator was slow and complicated. Later models replaced it with a hinged ramp between decks, faster and more reliable. Above the main deck, a modest superstructure housing crew quarters, the engine room, and the bridge. The crew complement was typically around 110 officers and men. The propulsion system used two diesel engines, General Motors 12-cylinder diesels producing 1,800 horsepower total, driving twin propellers and twin rudders. The propellers were protected by a tunnel hull design recessed into the bottom of the ship, preventing damage when beaching. The twin rudders provided redundancy. If one was damaged, the ship could still steer. Maximum speed was officially 11.5 knots, though crews would joke that was wildly optimistic. Most LSTs cruised at 9 knots. Some sailors claimed even that was generous, slow, ponderous. But then, this was never intended as a racing yacht. The ballast system was the engineering marvel that made everything possible. Enormous tanks built into the double-bottom hull and along the sides could hold over 900 tons of seawater. Pumps could fill these tanks in about 2 hours by opening valves that allowed seawater to flood in. Emptying took longer, about 2.5 hours, using diesel-powered pumps. When fully ballasted for ocean travel, the ship drew 14 feet, providing stability in rough seas. When pumped dry for beaching, the draft dropped to 3 feet 9 inches at the bow, shallow enough to approach virtually any beach. An anchor and mechanical winch system at the stern provided additional insurance. If the ship grounded too firmly and could not reverse off under engine power, the crew could deploy a stern anchor by motor whaleboat, literally winching the ship backwards off the beach. This kedge anchor system proved invaluable in practice, rescuing ships that had buried their bows deep in sand or coral. The armor and armament were minimal. The hull was welded steel, 3/8 of an inch thick on the bridge, not hardened, offering no real protection against shell splinters. The bow plates were 1 inch thick to absorb beaching impacts. Defensive armament initially consisted of a few 20mm and 40mm anti-aircraft guns. By 1945, the ultimate battery was 8 40mm and 12 20mm guns, still light compared to warships. LSTs were designed to get in, unload, and get out, not fight surface engagements. In March 1942, 7 months after Niedermayer drew his initial sketch, construction began. The first keel was laid at Newport News Shipbuilding in Virginia on June 10, 1942. This was LST-1, the prototype, but the Navy already knew they would need hundreds of these ships, maybe more than 1,000. Congress authorized massive construction programs in 3 separate acts dated February 6, 1942, May 26, 1943, and December 17, 1943. Originally, 1,152 LSTs were contracted for, with 200 scheduled for Lend-Lease to the British Navy. The problem was shipyard capacity. America's coastal shipyards were already building destroyers, aircraft carriers, cargo ships, submarines. There was no room for a massive LST construction program. Traditional naval doctrine said warships had to be built in established Navy yards with experienced shipwrights who understood the craft. Someone at the Bureau of Ships had a different idea. LSTs drew only 7 feet when unloaded. They could be built on rivers, inland, away from the coasts, in places that had never constructed anything more complex than barges and steamboats. The proposal seemed insane. Building ocean-going warships in cornfields? In places, like Pittsburgh and Evansville, hundreds of miles from the ocean. But the shallow draft made it possible. If you built LSTs on the Ohio River or the Illinois River, you could launch them there, float them downriver to the Mississippi, then down to the Gulf of Mexico, and out to sea through New Orleans. No need for deep-water shipyards. 5 inland shipyards were selected. The Dravo Corporation in Pittsburgh, Pennsylvania, at Neville Island on the Ohio River, the Missouri Valley Bridge and Iron Company in Evansville, Indiana, the Jeffersonville Boat and Machine Company in Jeffersonville, Indiana, also on the Ohio, the Chicago Bridge and Iron Company in Seneca, Illinois, on the Illinois River, and the American Bridge Company in Ambridge, Pennsylvania, on the Ohio. They were bridge fabricators and barge builders. They employed welders and ironworkers who understood steel construction, but not naval architecture. Dravo had built subchasers before, but nothing of this size. The Navy sent them Niedermayer's blueprints and said, build ships, build them fast, build them by the hundreds. The Cornfield Navy, as it became known, would produce 670 LSTs during the war, more than 2/3 of total American production. They did this by treating ship construction like building bridges, prefabricated sections, assembly line techniques, workers who specialized in welding one specific seam rather than traditional shipwrights who built an entire vessel from keel to deck. Dravo pioneered the techniques. They broke LST construction into major sections that could be fabricated separately, then lifted into place by massive cranes. Hull plates were cut to precise dimensions, pre-drilled for rivets or prepared for welding. Sections were assembled in jigs that ensured perfect alignment. Quality control inspectors checked every weld, every seam. The goal was not individual craftsmanship, but standardized mass production. The challenge was monumental. None of these yards had built ocean-going vessels before. Workers had to learn new skills. Welding hull plates on a ship is different from welding bridge girders. The stresses are different, the tolerance is tighter. Mistakes could mean ships that leaked, or worse, broke apart in heavy seas. The Navy assigned inspectors to each yard to oversee construction and ensure standards were met. On September 7, 1942, Labor Day, LST-1 slid down the launchways at Dravo Corporation into the Ohio River. Thousands of spectators lined the banks. They climbed trees. They gathered on rooftops. They had never seen an ocean-going warship launched in Pittsburgh. The ship looked bizarre, flat-bottomed, blunt-bowed, riding high in the water with ballast tanks empty. It looked like a rectangular barge with a tiny superstructure bolted on top. Someone called it an ugly duckling. The name stuck. The crowd whistled and cheered as the massive ship slid into the river, causing a wake so large that people scrambled up the banks to avoid getting wet. But the ugly duckling could float. It passed initial trials on the river. Then came the journey to the ocean, a voyage that tested the entire inland shipyard concept. LST-1 floated down the Ohio River to the Mississippi, then down the Mississippi to New Orleans. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The journey required modifying some bridges. The Navy established a ferry command specifically to manage this process, ensuring LSTs could pass under or through river obstacles. In some cases, bridges were temporarily raised. In others, LSTs waited for low water levels. The logistics were complex, but they worked. LST-1 reached New Orleans, underwent final fitting out at the Naval Section Base in Algiers, Louisiana, and was commissioned in December 1942, 4 months from keel to commissioning. The Navy immediately ordered more, dozens more, then hundreds. Now came the real test. Could this thing actually cross an ocean? Could it survive winter storms in the North Atlantic, where waves could reach 40 feet and winds exceeded gale force? And most critically, could it beach itself, unload, and extract cleanly without sticking or capsizing? The answer to that last question required overcoming 19th-century naval regulations. The Articles for the Government of the United States Navy explicitly stated, "He who doth suffer his ships to founder on rocks and shoals shall be punished." Running a ship aground was a court-martial offence. Officers who lost ships through negligent navigation faced disgrace and imprisonment. In early 1943, at Quonset, Rhode Island, Niedermeyer himself arrived to supervise testing. The commanding officer of the first LST delivered to the Navy for operational testing expressed extreme reluctance about the proposed test. Drive his ship onto a beach at full speed, 10 knots? That violated every instinct, every regulation, everything he had been taught about seamanship. Niedermeyer insisted. The ship was designed for this. The flat bottom and ballast system meant it would ride up onto the beach rather than ploughing in and sticking. The protected propellers meant it could reverse off without fouling. The hull could take the impact. Just do it. The commanding officer, facing a direct order from the ship's designer, complied. He approached the beach, ballast tanks pumped dry, draft reduced to under 4 feet, engines at full power. 10 knots, which for an LST felt alarmingly fast. The bow hit sand, and the entire ship shuddered. Rivets groaned, steel plates flexed. Then it rode up, and up. The bow climbed the beach gradient like a seal hauling out onto rocks, until it was resting on dry sand, the stern still floating in deeper water. The ship settled, level and stable. Bow doors opened, the ramp dropped with a metallic clang. Troops ran down onto the beach, trucks drove off. In less than 5 minutes, the cargo hold was empty. The ramp raised, the doors closed. Engines reversed. Water churned at the stern. The LST backed off the beach cleanly, propellers protected by the tunnel hull design. It spun around and headed back to deeper water. It worked. It actually worked. Naval officers who had been skeptical suddenly became believers. This ungainly, ugly, wrong-looking ship could do exactly what it was designed to do. By April 1943, LSTs were rolling off production lines at all 5 inland shipyards plus coastal yards. Newport News in Virginia, Charleston Navy Yard. The construction time had been reduced from 7 months to 4 months. By war's end, it would drop to 2 months. Some yards could complete an LST from keel to commissioning in 8 weeks. The ships were being built faster than crews could be trained to operate them. The program was given the highest priority. When an aircraft carrier's keel was laid at one yard, the Navy ordered it moved to make room for multiple LSTs. Landing ships were now more critical than capital ships. That decision tells you everything about how the Navy viewed amphibious warfare in 1943. Carriers projected power across oceans, but LSTs projected power onto enemy shores. Without the ability to land armies, carriers were just expensive targets. Crews called them large slow targets, LST. The nickname was affectionate and accurate. At 11 knots maximum, they were slow. Destroyers could make 35 knots. Even cargo ships made 15 to 18. LSTs wallowed along at less than 10 knots in practice. They wallowed in rough seas, rolling 40 degrees in swells that barely affected other ships. The flat bottom and wide beam made them handle like floating barges in a bathtub. Steering was sluggish. They had enormous turning radiuses. In high seas, they pitched and rolled sickeningly. Seasickness was epidemic. New crews spent their first week at sea vomiting. The motion was unlike anything experienced on normal ships. A destroyer rides through waves, cutting cleanly. An LST slams into them. Every wave was a jarring impact that resonated through the entire hull. Sleep was nearly impossible in rough weather. Men wedged themselves into bunks and held on. Hot food was a fantasy when the galley stoves broke loose from their moorings. Living conditions were cramped and austere. Officers shared tiny cabins. Enlisted men slept in tiered bunks with minimal privacy. The tank deck, when loaded with vehicles, reeked of diesel fuel and exhaust. Before opening the bow doors, vehicles would start their engines to warm up. The tank deck filled with fumes despite ventilation ducts that could be connected to exhaust pipes. Men breathed carbon monoxide and learned to work quickly. Fresh water was rationed. Early LSTs had limited desalination capacity. Showers were brief and infrequent. In tropical climates, the steel hulls became ovens. Ventilation was inadequate. Men slept on deck when possible, under the stars, because below decks was unbearable. In northern waters, the opposite problem. The ships were cold. Heating was minimal. Crew spaces were damp and chilly. Hypothermia was a real concern in winter Atlantic crossings. But they kept going. The ships were nearly indestructible. The hull was welded steel, massively overbuilt to withstand beaching. Out of 1,051 LSTs built during World War II, only 26 were lost to enemy action. 13 more were destroyed by accidents, groundings, or weather, including 6 lost in a single day in 1943 due to an ammunition explosion at West Lock, Pearl Harbor. The first combat test came in June 1943, the Solomon Islands, South Pacific. The first LSTs arrived as part of the island-hopping campaign against Japan. These were coral atolls with no ports, no docks, just beaches backed by jungle. Traditional landing methods would have required troops to wade ashore from smaller craft, leaving all heavy equipment offshore. The LSTs beached directly. Bow. Doors opened. Sherman tanks drove off onto coral sand and headed straight into combat. Trucks followed. Artillery pieces, supplies, everything the Marines needed to establish a beachhead came rolling off those ugly flat-bottomed ships in under an hour per vessel. Japanese defenders had prepared for traditional landing craft. They were not prepared for tanks driving ashore 60 seconds after the first LST beached. 1 month later, July 10, 1943, came the real test. Operation Husky, the invasion of Sicily. This was the largest amphibious operation of the war to that date. 4 American divisions, 4 British divisions, 1 Canadian division, over 3,000 ships and landing craft, including substantial numbers of LSTs. This would validate or condemn the entire concept. The invasion fleet included large numbers of LSTs, and they performed exactly as designed. At Licata, Gela, and Skogliti, where American forces landed, the beaches had no port facilities, just open sand and gravel. LSTs ran up onto the sand, opened their doors, and began unloading tanks within minutes of grounding. LST-2 landed its cargo so quickly that those same tanks participated in repelling a German counterattack on the beachhead the following day, July 11th. Without LSTs, those tanks would still have been offshore, waiting for smaller craft to ferry them in. With LSTs, they drove directly into combat while German forces were still organizing their response. LST 356 beached at Blue Beach in the Scent sector on the afternoon of July 10th. Within 1 hour, every tank and vehicle aboard had driven off. The ship then spent additional time unloading ammunition, gasoline, and supplies before retracting. During retraction, it grounded on a sandbar, rupturing a fuel tank in the auxiliary engine room, but the crew used the stern anchor and winch system, literally hauling the ship backwards off the sandbar. Within 20 minutes, LST 356 was free and returning to deeper water, damaged but functional. The official after-action report on Operation Husky described LSTs as outstanding in performance and usefulness. There were problems. Beaches became congested because not enough personnel were assigned to move supplies inland. Vehicles piled up on the sand. Underwater mines destroyed LST 313 on the first day when a German Me-109 fighter scored a direct hit. A bomb exploded below the tank deck, causing catastrophic damage. LST 312 was badly damaged by aerial attack. Several LSTs grounded so firmly they could not retract immediately, forcing them to wait for the next high tide. But the basic concept was validated beyond question. You could land armor directly onto an unprepared beach and sustain an invasion without capturing a port. This was revolutionary doctrine that changed naval warfare forever. Previously, amphibious invasions required seizing ports early. Planners had to identify which port the invasion would capture, then build the entire operation around taking it within days. The Germans knew this. They fortified every port on the French coast, turning places like Cherbourg and Calais into massive concrete fortresses with overlapping artillery coverage. They assumed any invasion would have to capture a port immediately or fail logistically within a week. The LST changed that calculation fundamentally. With hundreds of these ships, the Allies could sustain entire armies over open beaches indefinitely. No port required. Just find a stretch of coastline with a gradual slope, run the ships ashore, and start unloading. Build up forces faster than the enemy could respond. The Germans had prepared for the wrong kind of invasion. In September 1943, LSTs participated in the Salerno landings in Italy. The pattern repeated. Ships beached, unloaded, extracted, returned for more cargo. By late 1943, LSTs were everywhere. In the Mediterranean supporting the Italian campaign, in the Pacific island hopping across atolls, and accumulating in enormous numbers in Britain for the invasion everyone knew was coming. The build-up in Britain was staggering. By spring 1944, hundreds of LSTs crowded British ports. The Thames River, the Dart River, Plymouth, Southampton, Portsmouth. Everywhere you looked, flat-bottomed, ungainly ships sat at anchor or tied to docks, loading supplies for the greatest invasion in history. But before D-Day could happen, the crews needed training, realistic training under conditions as close to combat as possible. The British evacuated an entire section of Devon's coastline to create a training area. 3,000 residents left their homes and farms so American forces could practice assault landings. Slapton Sands was selected because it resembled Utah Beach in Normandy. Gravel Beach, a strip of land, then a lake. The geography matched. In late April 1944, Exercise Tiger commenced. 30,000 troops would practice the complete invasion sequence, from loading onto LSTs to landing under simulated enemy fire. The exercise included live ammunition. Cruisers and destroyers would fire over the heads of landing troops to simulate naval bombardment. The troops would experience the sounds, sights, and smells of battle, everything as realistic as possible, because in 6 weeks they would do this for real on a beach defended by German divisions. On the evening of April 27, 1944, 8 LSTs departed Plymouth and Brixham carrying vehicles and combat engineers of the 1st Engineer Special Brigade. This was Convoy T4, the follow-up force for Exercise Tiger. The LSTs were heavily loaded with trucks, tanks, jeeps, all with full fuel tanks and ammunition. The plan was to simulate the channel crossing by taking a roundabout route through Lime Bay, then land at Slapton Sands at dawn on April 28. Protection for the convoy came from the Royal Navy. 2 British destroyers were supposed to escort the Racine convoy. But HMS Scimitar had collided with an LST during previous exercises and was in port for repairs. The Americans were not informed that their primary escort would be absent. Only HMS Azalea, a corvette, led the 9 LSTs in a straight-line formation. The LSTs were operating on different radio frequencies than British ships, a communication error that would prove fatal. 9 German E-boats, fast attack craft based at Cherbourg, had left port shortly after midnight on a routine patrol. These Schnellboot were powered by 3 diesel engines producing 6,000 horsepower, giving them speeds over 40 knots. They carried torpedoes and 20mm cannons. The Germans had been alerted by heavy radio traffic in Lyme Bay and suspected Allied activity. Around 1:30 in the morning of April 28, the E-boats spotted the convoy. 8 dark shapes moving slowly in formation. LSTs, heavily loaded, making perhaps 8 knots. Perfect targets. The E-boats split into attack groups and closed rapidly. The LSTs had minimal defensive armament and no idea they were about to be attacked. British warning signals about E-boat activity in the Channel were never received because of the radio frequency error. The convoy sailed on in fatal ignorance. At approximately 2:07 in the morning, torpedoes began hitting. LST 507, at the rear of the convoy, took a direct hit amidships. The explosion ignited fuel and ammunition stored in vehicles on the tank deck. The ship became an inferno within seconds. Men trapped below had no chance. Those on deck jumped into frigid water. The sea temperature was 42 degrees Fahrenheit. Hypothermia would kill within minutes. LST 531, in the middle of the convoy, took 2 torpedoes in rapid succession. The explosions tore the ship apart. It sank in less than 6 minutes. Hundreds of men went into the water, many with improperly worn life jackets that caused them to float face down and drown. Others sank under the weight of combat gear. The darkness made rescue nearly impossible. LST 289 took a torpedo hit in the stern, causing massive damage but not sinking the ship. 13 men died, many more were injured. The ship limped toward Dartmouth Harbour, barely making it to safety. The remaining LSTs followed orders and scattered, zigzagging to avoid further torpedo hits. The E-boats, having expended their torpedoes, withdrew before British reinforcements could arrive. By dawn, HMS Onslow and other British vessels were on scene, pulling survivors from the water. 639 American soldiers and sailors died that night. Some estimates put the toll higher. 749 killed or missing. 2 LSTs were sunk. A third was heavily damaged. And this was not combat. This was a training exercise on the English coast. The disaster was classified immediately. Survivors were sworn to secrecy. The invasion was 6 weeks away. If the Germans learned about the losses, they might deduce the invasion target and timing. Security was paramount. News of Exercise Tiger was not released until after D-Day, buried in the much larger casualty reports from Normandy. But the Navy learned critical lessons. Radio communications were standardized across Allied forces. Better escort coordination was implemented. Troops received proper training on life jacket use. Plans were made for rescue craft to pick up survivors during actual combat operations. And critically, Vice Admiral Kirk of the U.S. Navy immediately recognized that E-boats posed a deadly threat to slow-moving LSTs. He demanded heavy air and naval bombardment of E-boat bases before D-Day. The E-boats had to be destroyed or driven from the Cherbourg area. D-Day, June 6, 1944. Operation Overlord, the invasion of Normandy. This would be the largest amphibious assault in human history. 5 beaches, stretching 60 miles along the Norman coast, over 150,000 troops landing on the first day. 7,000 ships and landing craft in the invasion fleet, and none of the 5 beaches had a functioning port. The logistics were staggering. Within 1 week, forces ashore would require 9,000 tons of supplies per day. Within 2 weeks, 12,000 tons per day. All of it coming over open beaches until Cherbourg could be captured and its demolished port facilities rebuilt. LSTs were absolutely critical to making this work. Over 230 LSTs participated in the initial D-Day assault and the build-up that followed. At Utah Beach, the westernmost American landing site, the first wave hit shore at 6:30 in the morning. LSTs began arriving shortly after, beaching in sequence. They unloaded tanks and trucks, then reversed off and returned to England for more cargo. The rhythm was mechanical: beach, unload, extract, repeat. 21,000 troops landed at Utah at the cost of only 197 casualties, remarkably low figures that testified to both planning and fortune. At Omaha Beach, 15 miles east, the situation was catastrophic. German defenses were far stronger than intelligence predicted. When LSTs arrived, they beached under devastating fire, but they kept coming. LST 393 beached on June 6th, unloaded Sherman tanks and supplies, then sat stranded as the tide went out. For 2 days, exposed to German artillery, unable to move, when high tide returned, the crew flooded ballast tanks and backed off. Over the next month, LST 393 made 30 round trips between England and Normandy. Each voyage carried armour and supplies forward, brought back wounded and prisoners. By August, over 1 million American troops, 250,000 vehicles, and 5 million tons of supplies had come ashore, most delivered by LSTs operating directly onto beaches. John Niedermayer died in 1988, largely unknown. His LST design enabled warfare that had never existed before. Power projection onto any coastline without ports. The ability to land armoured divisions on defended beaches and sustain them indefinitely. Wars are won by many things, but sometimes by a single good idea at exactly the right moment. A sketch that became 1,000 ships that won the war. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.